Okay, so I keep saying we're going to talk about equilibrium, and yet I continue to talk about kinetics and rates. We're talking about kinetics and rates only as a very brief introduction to kinetics and rates, because I really need you to know that equilibrium is defined as the rate of the forward equal to the rate of the reverse reaction. So we're continuing to talk about rates for just a tiny little bit longer so that we can define equilibrium and refine what equilibrium means, something being at equilibrium. So in our continuance of rate discussions, let's talk about the rate law. The rate law is a formula used to find the rate of a reaction. Here is a given reaction along with a partial plot based on those curvy plots that we've seen a few of at this point. The rate law for this reaction is as follows. Rate equals. Since the rate of a reaction really depends on the concentration of the reactants, the rate law only includes reactant concentration. So what we were writing in the last video were rate expressions, and I will try to be very consistent in my terminology. Those are rate expressions, but the rate law is written only in terms of reactant concentrations. So the rate law for this reaction is equal to rate equals concentration of reactant, this is the only reactant, times some value that is called the rate constant. So rate constant, little k. I know it sounds silly to talk about capitals and lowercase, but it's kind of important that this is a lowercase k. You'll see why soon enough. So the rate law is defined as rate equals k times the concentration of reactants raised to some power, raised to some exponent. That exponent is called the reaction order. That reaction order is typically a whole number, 0, 1, or 2 type number. For this specific reaction, the rate law is equal to k, where this is the value of k, this is the value of my rate constant, times 10⁵ to the first power. So being to the first power would make me call this a first order reaction. We'll talk about specifics of that in a bit. So if I try to define the rate at this specific concentration of 0.44 molar, that means I go over here and I find this little dot that's at 0.44 molar, and I determine, oh, the rate is 2.7 times 10 to the negative 4th molarity per second. Come on, clicky click. There we go. So this is the rate. What that's actually telling me is the slope of the line at that very particular point where the concentration is equal to 0.44 is 2.7 times 10 to the negative 4th molarity per second. How did you find K? We're not going there. We're giving you the briefest of introductions to kinetics right now so that we can jump on into equilibrium with both feet. So we're not worried about how to find K, but I'm showing you the rate law. That's what a rate law looks like. This is the rate of the reaction at that particular concentration. If it's at a different concentration, like this up here, which looks like 0.9, the rate is a bigger number. Okay. I said earlier that being a 1 means this is a first order reaction. I know we're presenting a very discombobulated set of information right now, but let's stay with it for a second. The rate law expresses the relationship of the rate of reaction and the rate constant to the concentration of the reactants, and only the reactants, raised to some exponent. So if you have this given favorite reaction of ours, you could see the rate law that looks like this. Rate is equal to K times the concentration of A, because it's a reactant, raised to the second power, times the concentration of B, because it's a reactant, raised to the first power. C and D are not ever found in rate laws. Product concentrations are not part of rates, period. These are reactants and reactants only. So because A is raised to the second power, we would say this reaction is second order in A. What that means exactly, we don't know yet. We're just introducing a couple of terms. We would say it's first order in B because B is raised to the first power. And we would say it's third order overall because you sum the exponents to get the overall reaction order. We can also see a zero order reaction. Something raised to the zero power means it's zero order. We'll talk specifics of that later. Okay, back to a slide that we just saw. Are you kidding me? No, unfortunately, I'm not kidding you. We saw this slide previously. We saw this little graph previously, and we said equilibrium is defined as when the rate of the forward is equal to the rate of the reverse. But wait, I just learned what a rate law is. And a rate law is equal to the rate constant times the reactant concentration raised to some power. So if I'm talking about the rate law of this reaction, that would be rate equals rate constant times reactant concentration raised to some power. And I'm going to put it as an X right now. That's the forward reaction. We're going to put a little F. That's the forward reaction. Well, the reverse reaction is this guy acting as a reactant. So that would be the rate of the reverse is equal to the rate constant of the reverse reaction times the times the concentration of the reactants. The reactants of the reverse reaction raised to some power. And I'm not going to put a power right there, although I'm about to when I do a little clicky-clicky. But if equilibrium is when the rate of the forward is equal to the rate of the reverse, I can set these two things equal to each other, like so. Rate of the forward is equal to the rate of the reverse. I put an X up here, but here I'm filling it in and telling you it's a 1, as in there's no exponent explicitly written. And here I wrote it as a Y. That kind of looks like a 4, but it's intended to be a Y. But here I'm telling you it's really a 2. So I can set those two rate laws equal to each other. The equilibrium is defined as when the rate of the forward reaction is equal to the rate of the reverse reaction. Always and forever. And so from this, I can manipulate things, and I'm not going to manipulate just yet. I can manipulate things to come up with a big K. That's the reason I was saying it's important that this is a little k. A big K, which is KEQ, also known as the equilibrium constant. So we will spend a lot of time talking about equilibrium constants this semester. But this is the crux of it all, knowing that equilibrium is defined as the rate of the forward equal to the rate of the reverse, and being able to write rate laws of the associated forward and reverse reactions. That's enough of a preview on that for now, but it'll be better defined in our next video. So what now? We've seen these plots again and again and again. I like repetition, but I'm not trying to bore you to death. We've called this the kinetic region and this the equilibrium region. In the kinetic region, what's happening? The forward and reverse rates absolutely are not equal. Absolutely are not equal. The rates are totally different in the kinetic region. But in the equilibrium region, they must be equal or you're not in the equilibrium region. The concentration of reactant and product are constantly changing in the kinetic region, but they're constant. They're consistent in the equilibrium region. Is that because the reaction has ceased, has stopped? Heck no! The reaction is sorry if that busted your eardrum. The reaction is still happening. It's just the rate at which the forward and the reverse are happening the same. Okay, stick a pin in me. I'm done with this one.